All right, now we are going to talk a bit about molecules. If we remember our levels of organization, remember the smallest unit of matter was the atom. And we've talked a bit about atoms now. We've talked about the protons and the neutrons in the nucleus. We've talked about the electrons flying around outside of the nucleus. And more specifically, we have talked about the electron shells. You know, the first shell holding 2 electrons, the second and third shells holding 8 electrons total each. Now remember, molecules are where we take our atoms and we combine atoms held together by chemical bonds to make a molecule. So a molecule is 2 or more atoms held together by a chemical bond. So we are going to be taking a closer look at these chemical bonds. We're going to see how we are going to be building these different biological molecules that are so important for life. So first, let's define a chemical bond. So a chemical bond is actually formed by the interactions between atoms that are trying to get those full electron shells. So remember when we talked about our atoms, we talked about how they want to have a full electron shell as the outer shell. And we talked about ions, about how if there are just a few, or 1 or 2 electrons in the outer shell, that those electrons, it's easier for those electrons to go away, to leave the atom, than it is for it to gain, 7 or 6 electrons. And so then that electron will just leave, and then it changes the charge of the atom. And then we saw the same thing if we had several electrons in the outer shell, but not quite a full electron shell, then it's going to try to gain electrons. So it'll pull in electrons, and then it'll fill that outer shell. So our chemical bonds are formed by interactions between atoms trying to get full electron shells. So again, our shorthand, we had the nucleus in here, and then we had our electron shells. So our first electron shell that had 1, 2 total electrons, the most in there. And then if we had more electrons, then we had 8 in there, so giving us 10 total electrons. And then we had the third electron shell, which also had a maximum of 8, giving us 18 total. And so again, if we were missing one of these electrons, let's say, then we would want to gain the electron, and then we would form either a cation, which is what, a positive or negative ion? Right, a cation is a positive ion meaning it has lost some negativity, making it positive, meaning it's lost one of the electrons, 1 or more electrons, making it a positive ion. And then we have an anion, which is a negative ion, which means we've gained electrons, which means we have more negativity than positivity. So we have more negative, meaning a negative ion or an anion. So when these atoms are trying to get full electron shells, we actually have different types of bonds that can form. And just as a side note, remember our noble gases don't form these bonds. So we don't see any bonding in noble gases because, remember, we have a stable outer shell. Their shells are already full. They're not trying to interact with anything. So the different types of chemical bonds that we are going to look at. First, we will look at ionic bonds. And this is where we are going to see this gain or loss of electrons. We have covalent bonds. Covalent bonds are a sharing of electrons. And these are the strongest bonds. And then third, we have hydrogen bonds. These are the weakest. And these are our partial charges, based on partial charges. And we'll take a much closer look at each of these different types of bonds. Before we look at the different types of bonds specifically, I want to talk about molecular formula. So we'll just scoot up here, and we're going to talk about what a molecular formula is first. So when we talk about a molecular formula, this is kind of a shorthand that's just going to tell us the number and type of atoms that we see in a molecule. So it's going to be shorthand. It's going to indicate, let's see, shorthand indicating the type and the number of atoms in a molecule. So it doesn't tell you how these atoms are arranged. It doesn't tell you what's connected to what. It just tells you how many they are and what they are. So for example, we have H2O. So this tells us that there are going to be 2 hydrogen atoms and 1 oxygen atom. So in this case, it's not telling us what's connected to what. Are the hydrogens connected to each other? Is the oxygen connected to one hydrogen, which is connected to a different hydrogen? That's a silly question once we talk about how they bond, but it doesn't tell us that. It just tells us 2 hydrogen and oxygen. Same thing if we talk about CO2, for example. We know that we have 1 carbon and we have 2 oxygens. Or if we talk about methane, which is CH4, we know that we have 4 hydrogens and we have 1 carbon. It doesn't tell us how these are arranged. It just tells us what we have, carbon and hydrogen, and how many we have of them. So that's our molecular formula. And our molecular formula is important, so we know what we have and what we're working with, but something that is related to that is an isomer. So an isomer are molecules that have the same molecular formula, but they have different structures. So molecules with the same molecular formula but different structures. So if we take, for example, C2H6O. So again, what we know is that we have 2 carbons, 6 hydrogens, and an oxygen. Now we can arrange these in different ways, and we can get 2 different molecules. So these would be isomers of each other. So if we arrange them in this way, let's see here. If we have a carbon bonded to a carbon in the middle here, so this line that I have between the 2 C's, between the 2 carbons, indicates a single bond. And so we're going to look closer at this. So far what we have kind of drawn, it would be looking like this. So this is our nucleus, and then we have our first ring of electrons around each of these, right? How many electrons does carbon have? Good, 6. So we have 1, 2, 3, 4, 5, 6. Whoa. Let me hang on a moment. Let me move this closer. This needs to be a little closer. One, 2. 1, 2, 3, 4. All right, so far the way that we have drawn atoms is we have had a red dot in the middle for the nucleus, which would be, our 6 protons in there, 6 protons. And then we have our 6 electrons flying around on the outside. And again, we know that we're missing some. We want to fill these in. And so far, what I'm indicating here with this one single line between the carbons is that right here we have a bond. And so this is a single bond, and we're going to look at that closer in just a minute, but I do want to talk about isomers first. So if we have our 2 carbons in the center that are bonded, and then we have those single bonded to hydrogens, and then we have the oxygen and another hydrogen here. This gives us our 1, 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and an oxygen. So that's one way that we could arrange these different atoms. Another way that we could arrange these atoms is if we had the carbon bonded to the oxygen that's then bonded to the carbon. So we have the oxygen in the middle instead of on the side here. And then we can add the appropriate number of hydrogens. So we have 1, 2, 3, 4, 5, 6 hydrogens, 2 carbons, and an oxygen. So you can see that with this single molecular structure telling us the number and the types of atoms, that we can arrange them in different ways. And the arrangement is very important because if they have a different structure, then they have a totally different function. So in this case over here, this is ethanol. And over here, this is dimethyl ether. And so then we're going to have different types of interactions with these different types of molecules. So these are examples of isomers here. Ethanol is an isomer of dimethyl ether. Dimethyl ether is an isomer of ethanol. And they both have the same molecular formula. All right, so before we get into any more of these kind of general structures, I want to go back to these different types of bonds. Now that we know what molecular formula looks like, we're going to talk about these different types of bonds, the ionic bonds, the covalent bonds, and the hydrogen bonds. So let's start off with our ionic bonds. Move this to the side here, and we'll talk about ionic bonds. So an ionic bond is where we have an attraction between a positively charged cation and a negatively charged anion. So attraction between a positively charged cation, and we've talked about cations, and negatively charged anions, and a negatively charged anion. So what we see is these are elements that are typically to the far left and the far right end of the periodic table of elements that are going to be forming these ionic bonds. So for example, let's take a look at sodium chloride, NaCl. This is our table salt. So if we take a closer look at table salts, so we've already seen we have our nucleus, and if we look at the periodic table of elements, we can see that there are actually 11 protons in sodium, which means if we have 11 protons, then how many electrons do we have? Right, 11 electrons. Now then if we look at our chlorine, which will be over here, if we look at the periodic table of elements, we'll see 17 protons, which means how many electrons? 17 electrons. We'll say sodium, chlorine. All right, so then what we want to do is we want to draw in our electron shells. So if we have 11 electrons here for sodium, let's draw in our 11 electrons. So first electron shell, which has 1, 2 electrons. Our second electron shell, which has, let's see, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not quite enough. 11. So we have our third shell, but our third shell isn't happy, right? Because we want to have how many? Right, we want to have 8 electrons in this outer shell, so we're missing 7 electrons here. Now if we look at our chlorine atom, we have 17 protons, which means we have 17 electrons. We can draw these in. Our first electron shell, 2 electrons. Second electron shell, 3, 4, 5, 6, 7, 8, 9, 10. Third electron shell, 11, 12, 13, 14, 15, 16, 17. Now, is this one happy? Does it have a happy full outer shell? No, right? It's missing 1 electron here. So remember we talked about when we were talking about ions, either gaining or losing electrons, and then that makes them happy because they have this stable outer shell. So if we look at sodium, what do we think is going to happen with sodium? We have one single electron in the outer shell. We have to either gain 7 electrons to make the outer shell happy or lose an electron. Right, so we're going to lose this electron. If we get rid of that electron, then we completely get rid of that third shell. We get down to this second shell, and if we get down to this second shell as our outer shell, then it's happy because it has a full electron shell. Now what about over here with our chlorine? We're only missing 1. Right, so is it easier then to lose all 7 that we have in the outer shell, or is it easier to gain 1? Right, it's easier to gain 1. And so then we can see that if that happens, then we have an outer shell, which is our third shell, that will then be happy with its 8 electrons. And so this is what we see here with sodium and chlorine, is that our sodium is going to lose an electron, get rid of it so it has a stable outer shell, which is the second shell, and our chlorine is going to gain that electron that the sodium loses. Now when that happens, remember that makes our anions and cations. So our sodium, if we lose negativity, makes a positive ion, which is our cation, and then our chlorine, when it gains that electron, is going to be more negative, so we have a negative anion. Now when this is positive, and this is negative, then they form an attraction to each other, kind of like a magnet. We have the positive side, we have the negative side, and they want to be close to each other. So then what happens is, even though there isn't an actual sharing of electrons, there isn't something that's holding these two together, there is something holding them together, and it's this attraction between the two, because the sodium is so positive, the chlorine is so negative, that they stay next to each other. And this is what we see. We then have our molecule, which is sodium chloride. Positive sodium and negative chloride. So this is an ionic bond, an example of an ionic bond. If you want to do your own example, you can try magnesium oxide, MgO. So you can take magnesium, draw out the electrons, takes oxygen, draw out those electrons, and you can see another interaction where we're gaining and we're losing electrons. So this is our ionic bond. And so our cations is what we're looking at here. And because they're so positive and negative, because they've gained and lost electrons, they end up staying next to each other, and they form a crystalline structure. So we have lots of, let me draw that in here. So we have lots of sodiums that are positive next to chlorines that are negative. And so then what ends up happening is we have these negative chlorines that are surrounding the positive sodium, but then we have the positive sodium surrounding the negative chlorines. And then we have what we see as table salt. Sodium chloride is table salt, which is a crystalline structure. We can have big chunks of table salt. And that's because we have all of these positive and negatives, and they're all forming this kind of crystal structure, this solid rock-like structure. Okay, so we're going to move from our ionic bonds to the second type of bond, which is our covalent bonds. So our covalent bond, we have already mentioned, is a sharing of electrons. So this is where we have our atoms share a pair of electrons. So this is one from each, one electron from each atom. And it is stronger than an ionic bond. So in an ionic bond, we're either gaining or losing electrons to form the bond. In a covalent bond, we're sharing electrons. And so atoms can share either one pair of electrons, 2 pairs, or 3 pairs. So 1, 2, or 3 pairs of electrons, and that's going to give us either a single bond, a double bond, or a triple bond. And the number, so the number of covalent bonds that are possible, so whether we're going to have single bonds, double bonds, triple bonds, how that will work out, is due to the number of spaces that are available in the outer shell. So if we look at, let's say, H2O, water, right? We know, given the molecular formula, that we have 2 hydrogens and an oxygen. So let's draw out our oxygen. So here's our nucleus. If we look at the periodic table of elements, perhaps you can find how many protons we have in the nucleus. 8 protons. So if we have 8 protons in the nucleus, how many electrons do we have? Good, 8 electrons. So let's go ahead and draw in our electrons. Our first shell again with our 2 electrons maximum. And then we have our second shell, which is going to give us the rest of our electrons. So 1, 2, 3, 4, 5, 6, and then I'm going to put these down here, 7, 8, just for illustrative purposes. So we have our 8 electrons. Now if we look at our outer shell, is it happy? Is it stable? Do we have all 8 in the outer shell? No, right. How many are we missing here? Right, 2. So in this case we could say, okay, oxygen isn't happy. It wants to have a stable outer shell. In order to do that, it needs to either gain 2 electrons or lose 6 electrons. Or what it can do is it can share electrons with other molecules, or with other atoms. Sorry, not molecules. It can share electrons with other atoms. And so then what we see here, in the case of water, is it's going to share electrons with hydrogen atoms. So if we draw a hydrogen atom, we have our nucleus, and if you look at the periodic table of elements, hydrogen has 1 proton. If it has 1 proton, how many electrons? Good, 1 electron. So if we have our 1 proton, we have how many shells? Just 1, right? Because it has 1 electron. Now, I drew it here on purpose. Let me draw one separate first, right? So if we draw our hydrogen atom to begin with, it would just be 1 proton here in the middle. And then we have our single shell, which has 1 single electron. But it's not happy, is it? No, because it's missing an electron. It wants to have 2. Its outer shell is the first shell, and it wants to have 2 in that outer shell. Since it doesn't, it's going to be either wanting to lose an electron, which would make it very unstable, or it wants to gain an electron. In this case, we see that it wants to share an electron. So here, what we see happening is that it's going to end up forming a covalent bond with oxygen. And so it's 1 electron that it has. I'm going to clean this up a bit here. Is going to be shared. So here we had the 1 electron that came from the oxygen, and then we have 1 electron that comes from the hydrogen. And then they're going to share that to make a bond. So a bond, again, is 2 electrons. So in order to have a shared electrons, they have to be in pairs to make a bond. And so then we see the same thing with our second hydrogen. We have our nucleus with our 1 proton, and then we can draw in our 1 single shell, and we have the hydrogen that came from the oxygen, or the electron that came from the oxygen, the electron that came from the hydrogen. And so then what we see here is we have a bond here, and this is a single bond, because a single bond includes 2 electrons. You see the same thing here. We have another single bond, which includes 2 electrons. So this is our H2O, hydrogen bonded to oxygen, which is bonded to another hydrogen. And I can draw that a little bit differently so it kind of looks similar to what we see here. So what we see here, whoops, is we have the oxygen, right, that's this big guy here, connected to the hydrogen up here, and connected to this other hydrogen over here. And that's our H2O, is water. So these are covalent bonds. Covalent bonds are a sharing of bonds. So we can look at another example, maybe a little bit more quickly. So if we look at methane, for example, which is CH4. Now we know we have 1 carbon and 4 hydrogens. If we draw our carbon, here's our nucleus. How many protons in the nucleus? It's 6. You should know that for carbon, which gives us how many electrons? It's 6. We can draw in 1, 2 here. 1, 2, 3, 4, 5, 6. So that's our 6 electrons. And again, then we're missing 1, 2, 3, 4 electrons. Those are going to come from our hydrogens. So here's the nucleus of 1 hydrogen with its single shell. It's going to share its 1 electron with the carbon. Then we have another hydrogen over here. It's going to share its single electron. Another hydrogen over here shares its single electron. And another hydrogen over here sharing its single electron. So then we have our electron pairs on the outside, and everybody's happy, right? Our hydrogens have a full outer shell. They have 1 shell and it's full with 2. And then our carbon is happy because it has a full outer shell. It has 8 in its outer shell. And so everything is stable. Everybody has a happy outer shell and everybody's happy with where they are. Now, what does this mean exactly with the electrons? What does it mean to share? We get in an ionic bond where we steal an electron or we get rid of an electron. And remember, the electrons are clouds, right? So we have the nucleus, which of course contains the protons and neutrons. And then we have the electrons flying around. So they're actually flying around very, very fast all of the time. Flying around, flying around, flying around in their shells. Now when we're talking about our ionic bonds, we have our cation over here, our anion over here, and then we have the electrons over here, and the electrons over here, and one happens to be more positive, one happens to be more negative, and then they hang out next to each other because of that. Now, when we're talking about covalent bonds, we're talking about sharing electrons, and what that means is that we have the electrons are going to be going around here, and then they're going to be going around here also, and they're sharing them. So the electrons are flying around the hydrogens, flying around the carbon, and since they move so fast, everybody feels like they are stable because they all feel like they have the electrons that they need in their outer shell. And so you can see as I'm kind of flying around as electrons here that everybody has their stable outer shells because the electrons are flying around in these clouds and everybody feels like they're getting their fair share of the electrons. Now we do have things that complicate it a little bit more, and we have 2 different types of covalent bonds. And this is called polarity. So we have 2 different types of covalent bonds, and this is whether or not the atoms share the electrons evenly. So whether or not they share the electrons evenly or not. So let's take a minute to think about why it would share an electron evenly or not share an electron evenly. In atom, the nucleus itself is going to be pulling on the electrons, right? So we have the nucleus, and then we have the electrons flying around, and they're going to be pulled toward this nucleus a certain distance. So we have the first shell, and then we have the second shell, which isn't exactly looking like this in real life, but we can just draw it this way, and then we have the third shell. So these are being pulled on the nucleus in a certain amount. Now there are some elements that are going to pull on electrons more than others. So an atom's ability to attract the electrons is called electronegativity. We're going to come back to polarity in just a minute. So electronegativity is the atom's ability to attract electrons. So if we look at the periodic table of elements, and the atoms to the right and top of the periodic table are going to attract elements more strongly. So these are more electronegative. And over here then, we have less electronegative. So when we look at the periodic table of elements, for example, some things that we have up here, we have fluorine up there, we have oxygen up there, nitrogen, chlorine, carbon is up here, boron is up here. Over here, up in the top, so it's a little bit more electronegative, is hydrogen. But then down here we have sodium, so not very electronegative, magnesium, not very electronegative, beryllium. So those that are over here, so down and to the left, are going to be less electronegative, meaning it's not going to pull on the electrons as much as those are in the upper right-hand corner. So, for example, oxygen is going to be pulling electrons toward it a lot more than hydrogen, for example. Hydrogen is in the upper left, oxygen is in the upper right, meaning it's more electronegative. So what we see is an unequal sharing of these electrons in a covalent bond. So remember, ionic bond, they're not sharing at all, so it doesn't matter how hard they pull on it. So then what we end up having are two different types of bonds. We have what are called nonpolar covalent bonds. And if it is nonpolar, that means that they do share them evenly. So atoms in the bond share electrons evenly. So the electrons are attracted to both atoms about equally. So it doesn't always have to be the exact same atom, but it can be like a carbon-carbon bond, or H2, which is a hydrogen-hydrogen bond. So if it's hydrogen attached to hydrogen, then of course we're going to see these electrons flying around the hydrogen in equal amounts. Nothing's going to be pulling harder than anything else because it's the exact same thing. Now, we can see, C2 is a nonpolar bond, O2 is a nonpolar bond, N2, so these are all the same thing, right? Because if, one oxygen is not going to be more electronegative than another oxygen. One thing that's absolutely important that you understand is that carbon-hydrogen bonds are nonpolar. Even though carbon is in the right side of the periodic table and hydrogen is on the left side, they're at about the same electronegativity, which means that they're not going to be pulling on the electrons any more than the other. So carbon and hydrogen are nonpolar. When they're next to each other, when they form a covalent bond, they're a nonpolar covalent bond. So they share them equally. Now the other kind of bond then, of course, is a polar covalent bond. So this is then where the atoms in the bond share electrons unevenly. So the electrons are more attracted to one atom than the other. So then what they do is they spend more time near one atom. So where we would see this, for example, is if we have an oxygen atom and a hydrogen atom. Hydrogen is less electronegative than oxygen. So oxygen was in the upper right-hand corner, hydrogen is in the upper left-hand corner. And so when we have our electrons flying around, they're going to spend more time around the oxygen than they spend around the hydrogen. So you can see I'm circling the oxygen a whole lot more than I'm circling the hydrogen. And that's exactly how it is. They're pulled toward the oxygen and pulled toward the oxygen and pulled toward the oxygen. So the hydrogen gets a lot less time with the electrons. It still feels like it's satisfied with its electron shell, but it doesn't get the electrons as much as the oxygen does. What this does then, if you can even look at this image that I've kind of drawn here, is it ends up making one side of this covalent bond a lot more negative than the other side, or at least slightly more negative. Not a lot more, because if we're talking about a lot, maybe we're talking about ionic bonds. But when we're talking about an uneven sharing of electrons, then one side has a slight negative charge, and then the other side has a slight positive charge. So if we're spending more time on one side, is that going to have a more negative charge or a more positive charge? Right, more negative charge. So this little guy here, this is our partial sign. So we're saying that it's partially negative over here by the oxygen and partially positive by the hydrogen. So this is our polar bond. If we have electrons spending more time over here, this side tends to be more negative than this side, because the electrons, which are negative, are not spending as much time over there. So we have this causes a slight negative charge on one side of the bond, and then therefore a slight positive on the other. So then this is what a polar covalent bond looks like versus our nonpolar, where we're sharing evenly. We don't have more electronegative charge. We don't have more negativity on one side. It's much more even. So some examples of our polar covalent bond, we just saw one, OH. That's an example. Carbon-oxygen bond, nitrogen-hydrogen bond. Those are some other examples of electronegative, or where there's one that's more electronegative than the other. So we have a partial positive, partial negative, making a polar covalent bond. All right, so now that we have discussed our ionic bonds and our covalent bonds, and even more specifically the two different types of covalent bonds, which are the nonpolar covalent bond and the polar covalent bond, now we're going to spend some time on our third type of bond, which is the hydrogen bond. Now the hydrogen bond is a little bit different than the other bonds, of course. This is a weak bond, and it's a temporary bond. So it's a temporary interaction between polar molecules. And so now we've just talked about polarity, and any molecule that has this uneven sharing, that has a polar covalent bond, is called a polar molecule, because we have this partial positive, partial negative. So when we talk about hydrogen bonds, we see this in water. So if we look at water, which is our H2O, we can use our stick model here. So we have our oxygen, and it's attached to two hydrogens. Actually, we'll draw it out here with our electrons too. So if we look at our oxygen, it has 8 protons, which means, of course, it has 8 electrons. We can draw those in. First shell, 1, 2, 3, 4, 5, 6, 7, 8. And then we can draw in our hydrogens. We've already done this, so I'm kind of going quickly. All right, so this is what our H2O looks like. So our two hydrogens, 1 proton each here, 8, and then they're sharing. So remember that our bonds between our oxygen and hydrogens are polar. So water is a polar molecule, which means, of course, that if we look at this oxygen bonded to the hydrogens, if we look at our electrons, they're going to spend a lot more time around the oxygen than they do around the hydrogens. So I can do a little illustration here, a lot more time around the oxygen than the hydrogens. And you can see that then we have, of course, our partial negative here, partial positive here, partial positive here. So we have our polar molecule, we have a lot more negativity in this direction than in the other directions. So then what we see with our hydrogen bond is utilizing this polarity. So when we're talking about the hydrogen bond, we have this partial positive end on the hydrogens attached to this negative end of the oxygen. And so then what we see is that we have our oxygen, partially negative, partially positive, and then we have this temporary bond between the partial positive of one hydrogen and the partial negative of the other oxygen. So it's not within the H2O molecule itself, it's with another water molecule. So this right here, the dotted line, is our hydrogen bond. Again, it's weak and it's temporary, so it's ever changing and ever moving. So then we have, let's say, another water molecule here. With its partial negative, we have a bond formed here. Partial positive, partial positive. And then let's say we have another water molecule here. Again, our hydrogens are partially positive, our oxygens partially negative. We have this temporary bond between this partial negative of the oxygen, partial positive of the hydrogen, and so they're attracted to each other because of these partial negatives, partial positives. So the oxygen is pulling the electrons from the hydrogens in its own water molecule, making it more negative, which then makes it more attracted to this partial positive of another hydrogen on another water molecule. And so then what we see is these water molecules are held together by these weak hydrogen bonds. And so we see this in water, and we're going to talk a lot more about water in the next section, and the different properties of water, but this is what gives water its surface tension. It's these bonds that are forming and breaking and forming and breaking and forming and breaking, because we have a lot of these H2O molecules that are floating around in one area. And so we have these hydrogen bonds that are forming and breaking. However, hydrogen bonds are not just related to water. So if we remember back to our example of our ethanol, for example, which was our two carbons, we had our hydrogens, and then we had our oxygen-hydrogen bond there. Now recall that these bonds here, the carbons and hydrogens, are nonpolar. So all of this equals out to 0. There's no polarity there. However, here we have the same type of thing that we see in water. We have this oxygen-hydrogen bond. And so then we see the same thing where the electrons are being pulled more toward the oxygen than the hydrogen. And then what we see is, in the case of ethanol, this is a polar molecule. Even though this part is nonpolar, this is a polar molecule because it has this partial negative, partial positive. And then, if we had some water here, we're going to see an attraction. We're going to see this weak hydrogen bond form between this partial negative of the oxygen and partial positives of the hydrogen. And then it can form, and it can break, and it can form, and it can break over and over and over again, as we see in hydrogen bonds. So that summarizes our atomic bonding and our molecules. So just again to kind of go over it, our molecules are two or more atoms that are held together by chemical bonds, and then we define chemical bonds as this interaction between atoms that are trying to get their full electron shells. And then we looked at the different type of bonds. So we had our ionic bonds, where we either gain electrons or lose electrons, and then when that happens, we end up with our cations and our anions, which are going to stay next to each other because they're positive and negatively charged. Then we have our covalent bond. Our covalent bond had two different types of bonds. Both share electrons, but depending on the electronegativity of the atoms involved, we either have a nonpolar covalent bond, which is meaning that they share them evenly, or we have a polar covalent bond, which means they share them unevenly. And so then we have this partial positive, partial negative. And that's a polar molecule then. And then we have our hydrogen bonds, which are weak temporary interactions between polar molecules. The best example that we have of that is water, where we have this partial positive, partial negative, and we have this ever bonding and breaking and bonding and breaking between our water molecules.